As promised, I'd like to start this video with giving you the answers to these 4 exercises I assigned to you at the end of the last video. I'm not going to go through them with quite the level of detail that we did in the last video, but I will give you answers for checking your work. In this first exercise, A is assigned a value, 1.75. The second line is going to assign to A the value of whatever is over here on the right. So we need to come up with an exact value here before we can assign it to A. So we take the previous value of A, which is still at this moment the current value of A, which is 1.75, and we add 2 to that, giving us 3.75, and that is the new value that is stored within A. So when we reach this line in the code, we take the current value of A, 3.75, multiply it by 2, giving us 7.5, and that is the value that is then stored into A. So when we print A, we should see 7.5. For example 2, we now have 2 variables, B and C. B is assigned a value of 3, C a value of negative 4.2. Then C will be assigned a new value in the third line, and that new value will be whatever the current value of C is, plus whatever the current value of B is. The sum of these two numbers would be negative 1.2, so we should expect this line to print negative 1.2. Over here on the right, making things more complicated still, we now have 3 variables, W, X, and Y. W and X are declared with these initial values of 2.1 and 3.4. In this third line, we're declaring a new variable called Y, and Y is assigned the value of X. So Y is given this value of 3.14. In the fourth line, X is then updated to receive a new value. X is assigned the value of W, the value of W being 2.1. At this point, there's something of a question going on. In some sense, you might have thought of the variable Y as being introduced to just be a copy of X. And if X is then changed in the next line, you may think that Y gets changed along with it. But if that's what we wanted, then the computer is unaware of that. The computer only knows that we wanted to copy X one time, and does not assume that we wanted to copy X always and forever. So the value printed for Y here is the value that it was given just this one time, 3.14. The last example, we have a couple of things going on here. Z is our variable, and it's assigned a value of 3. At the next stage, Z is going to be assigned a new value. It's going to be assigned a new value which is equal to whatever the current value of Z is multiplied by Z squared. Recall that it's going to look up the previous value of Z when it does this square computation. So this Z squared should evaluate to a 9. And then what will happen is that Z, its current value, which is 3, will be multiplied by 9 to give us 27, and then Z will be assigned the value of 27. So just to summarize, the values we would expect to see if we ran this code in Python would be 7.5, negative 1.2, 3.14, and 27. So let's pop on over to REPL actually and just run this code, which is the quickest way to find out the answer. Here is that code, and when we run it, we get almost all of those answers, but something different is happening for C. We thought we should get the value of negative 1.2, and what we've actually gotten is negative 1.2, 0, 0, 0, 0, 0, many zeros, followed by a 2. And that's surprising, but is something that we'll have to deal with the floating point data type in Python. If I clear away all of this code, I can show you a more simple example of this phenomenon. I'm just going to ask Python to print 0.1 plus 0.1 plus 0.1 if that is equal to 0.3. Mathematically, I feel very confident that 0.1 plus 0.1 plus 0.1 is equal to 0.3. But when I run this code, the computer tells me that that is false, and that's very strange. So I'd like to explain what is going on here. A computer has only so much memory and so much space. It cannot deal with any notion of infinity, and unfortunately, decimals and fractions and mathematical numbers, many of them do require infinity in order to be represented. Pi is an example of such a thing. Its digits go on and on and on forever. A more simple example of such a thing is 1/3. It's just 0.3 repeated over and over and over and over again. A computer cannot hold on to that notion of infinity, so somewhere it's going to have to truncate, cut off that forever repeating, and just take an approximation of 1/3, 0.3 some number of times before it stops, and say, this is my representation of 1/3. It's not exactly 1/3, but it's close enough. What this can do is lead to weird types of computational errors. So in general, one of the things you'll want to think about with floating point numbers, you'll have to keep in mind that this round-off error exists. It can be very problematic to have two different floating point numbers that you think or even know mathematically should be equal, and to ask the computer if they're equal. You're going to have to be a little bit more clever, maybe looking at the difference of the two of those numbers and making sure that it's particularly small instead of checking for equality. That's a much better programming practice because weird things are going on in the background, and there can be errors in totally unexpected places. For example, 0.1 is very finite. It is not an example of a fraction that goes on forever. And so it seems very strange that we would have a round-off error with 0.1 plus 0.1 plus 0.1 is equal to 0.3. But these errors can happen in seemingly unexpected places for very interesting reasons. So in my next set of slides, I'm going to go a little more in depth into what's happening with that 0.1 error. It's an optional set of slides, but I think it's absolutely fascinating.